The fourth and weakest of the intermolecular forces is known as London dispersion forces. This one goes by lots of different names. You'll also see it called just London forces or just dispersion forces, or the general chemistry textbook that I used called these van der Waals forces. And so you will see all sorts of different names for these. I will do my best on quizzes and tests to always call it by both names, London and dispersion, but every once in a while I mess up and I'll either say just London forces or dispersion forces. Don't be confused by that. It's like saying dollar and buck. It's the same thing. These intermolecular forces are found in every possible substance because it is due to the random motion of the electrons in the substance. And every substance has electrons. They move randomly. Therefore, every substance has these London dispersion forces. So here's what's going on with the London dispersion forces. Let me see if I can grab the laser pointer. Here we go. All right, most of the time in a substance, the electrons are very randomly arranged, and so we draw these electron distributions that just have a uniform color throughout the molecule. But every once in a while, just due to the random motion of the electrons might move to the left side of this molecule just for an instant. Well, if we have more electrons on the left side than on the right side, the left side's negative, the right side is positive. And again, this is due to random motion of electrons. So this just lasts for an instant. But it does last long enough that this positiveness here on this end of the molecule affects the electrons in the adjacent molecule. And so for just the next instant, electrons in that right-hand molecule are attracted over to that side, making that end of the molecule negative. So there's an attraction between these two molecules. And then you blink and it's right back to a uniform distribution of the electrons. So nearly all of the time the electrons are nice and uniformly distributed, but just instantaneously these dipoles form, and in the next instant they're just gone. So London dispersion forces are often referred to as instantaneous dipoles, and it really is due to just that random motion of the electrons. And so that means that these intermolecular forces are present in every substance, regardless of what the substance is. The strength of London dispersion forces depends very much on the nature of the molecule. There's a concept called polarizability, which is a mouthful. Say that 3 times fast. I think of this as being the squishiness of the electron cloud. If it's really easy to kind of push the electrons around and slide them over to one end of the molecule away from the opposite end, then it's a very polarizable molecule. So it's just how easily can we distort the electron cloud of the entire molecule to make that electron distribution asymmetric. The more polarizable or the easier it is to do this, then the stronger the London dispersion forces. And if we are comparing two very similar molecules, such as iodine and fluorine, right? These are both the Brinkelhoff elements that form these diatomic molecules. So iodine is I2, fluorine is F2. And these are both halogens, so it's a single bond between each of the atoms. Well, in iodine, which is a much, much larger atom than fluorine, those electrons are located much further from the nucleus than they are in fluorine. If you think about that in terms of the orbitals, the outermost electrons in iodine are in a p orbital that's much farther away from the nucleus than the 2p orbital from the fluorine outermost electrons. And these electrostatic interactions are inversely proportional to distance. So in iodine, where those electrons are farther away from the positive nucleus, that attraction is greatly reduced. And so it's really easy to squish around the electrons in iodine and not so much to squish around the electrons in fluorine. And so that makes iodine much more polarizable than fluorine. That means that the London dispersion forces in iodine are much greater than those in fluorine, and that's why iodine is a solid at room temperature and fluorine is a gas, because the boiling point of iodine is much higher because it has stronger intermolecular forces. Ditto for the melting point. The strength of London dispersion forces also depends on how many electrons are present. More electrons means more polarizability, and that goes hand in hand with having more atoms in your molecule. So for instance, if we were to compare pentane, which has a chain of 5 carbon atoms and an additional 12 hydrogens, versus a chain of decane, which has 10 carbon atoms and 22 hydrogens, the boiling point of decane is going to be much higher because we have a lot more electrons in decane than we do in pentane, and so those London dispersion forces are much stronger. Just to look at the straight chain alkanes, which pentane and decane are part of the family. If we look at the number of carbon atoms that are in the chain, this graph is showing us how the boiling point climbs as the number of carbon atoms climb. That's largely due to having stronger London dispersion forces as these chains get bigger. The third factor affecting the strength of London dispersion forces is the shape of the molecules. If we have a linear molecule versus a more spherical molecule, which is also referred to as a branched molecule, we're going to have a difference in the London dispersion forces. The linear molecules have more opportunity for one molecule to interact with another molecule along the length of that chain, whereas this branched molecule that's almost spherical in shape, even though it has the exact same number of atoms as the molecule on the left, it's going to not have as strong of London dispersion forces because there's not as much opportunity for this molecule to interact with an adjacent spherical molecule. To wrap up this video, we wanted to list and describe the 4 types of intermolecular forces, starting from the strongest and going to the weakest. They are ion-dipole, hydrogen bonding, dipole-dipole, and London dispersion forces. We wanted to still distinguish intermolecular forces from chemical bonds. So these are the forces between one molecule and the next, where the chemical bonds are the attractions within a molecule that hold that molecule together. And then we continue to relate these basic properties like boiling point to the intermolecular forces. The stronger the intermolecular force, the higher the boiling point.